Hello again. Now we'll continue our look at meta-analyses and systematic reviews. So in this module we'll cover the technique of meta-analysis in much greater depth than was offered before. Hopefully by now I've sold you on the concept, but now you get to see under the hood. You get to see how meta-analyses work. Now it's not the expectation that all or even most psychologists will go on to conduct a meta-analysis themselves. You might, but chances are probably no. But you should be able to read a meta-analysis in a considered fashion rather than slavishly accepting their conclusions unquestioningly. I like to use the metaphor of a sheep here. Don't be like the sheep and follow the herd. So as part of this module, you'll be assigned a meta-analysis from your chosen discipline to read and reflect on. I'd highly encourage you to engage in this activity as it lets you put the skills you've learned into practice. Okay, so let's go through the steps for conducting a meta-analysis. So the following steps are traditionally performed to answer a research question. Firstly, you conduct a thorough, systematic search of the existing research literature to identify candidate studies. And as I mentioned in the first module, there are risks when you present a selective meta-analysis because it means you're not presenting the full picture to the reader. You need to examine each article carefully, noting details about the type of sample, the instruments used in measurement, and the outcomes assessed. Now you record this information usually in a logbook or in a spreadsheet so that you can include it for the actual publication. Now most meta-analyses will examine a single outcome, but the studies that you're investigating might well report others that were investigated. For example, if you're doing clinical work, you might be investigating depression, but the study also investigated, say, anxiety and general well-being. You then calculate the effect size of the group difference, say treatment and control, or the correlation. You then enter these details into a spreadsheet or a statistical package for analysis. It used to be these were formed by hand. Gone are those days, thank goodness. A computer will speed up this process considerably, and there really is no need for a high degree of mathematical proficiency to conduct a good and worthy meta-analysis. So the goal of a meta-analysis is to combine effect sizes across studies. Once data on the sample size and the magnitude of the effect under investigation has been collected, the meta-analysis seeks to combine them for what's called a summary effect size estimate. Now typically this would be the mean weighted effect size across studies, so that larger studies carry more weight than a single small study. But if there are concerns about a single study dwarfing the others, an unweighted effect size should also be offered. Now it's not uncommon to find in a meta-analysis the weighted and the unweighted effect size given. Typically these won't vary too much and you should reach the same conclusions. Now, if there's strong variability in effect size or concern over outliers, sometimes we'll also report the median. Now, if you remember back to your first year statistics course, The median is resistant to the presence of outliers and presents a more balanced view if you have either a high degree of skewness or the presence of one or two large outliers. Now, a visual depiction of the distribution of effect sizes should also be presented. This is to show the degree of variability across studies and to convey this to the reader. Now, there are many ways to display information about effect sizes. Older studies might simply present a stem and leaf plot. And if you're familiar with the way that stem and leaf works, we have the stem here, and then each of these individual data points represents the stem. So you pair, the leaf. You pair the stem and the leaf together. So this shows that the effect size was 0.31 for one study, 0.34 for another, and 0.39 for the further. If you tilt your head, and this is something I always used to teach my first year stats students, if you tilt your head 90 degrees to the right, that actually resembles a histogram. The other option, of course, is to present a graphical depiction like a histogram. Now you can see here a histogram I've used from one of my meta-analyses. And I wanted to make it really, really clear to the reader that the null effect would be here and all my effect sizes fell to the left of the null. So it was a study on gender differences in reading and writing, and women traditionally score higher on those types of tasks. So if you are going to present a histogram and you have a null hypothesis that you want to refute, I'd highly suggest you make that visible to the reader, because often when people view a histogram, it's a little bit hard to interpret depending on where the axes start, and that's a nice, easy way of demonstrating it. Now, another common graphical display you'll encounter is called the forest plot. This includes information on the sample size used, as well as the confidence intervals of the estimate. Now you can see here that the square used in each study indicates the sample size of that study relative to others. So if we have a look at that first row there, it was a very, very small sample size compared to the others. You'll also notice that the horizontal line's extremely wide, so there wasn't much precision with that estimate. The confidence intervals were quite large. Generally, if you have a larger sample size, then you'll have tighter confidence intervals. Now, another way of doing the forest plot is something like this, which is generated with the comprehensive meta-analysis software package. It actually presents the standardized mean difference here on the left for each study, as well as the associated probability value, the test of the null hypothesis, as well as integrating our forest plot information here. So that's another way to present the data, and you can present it along that descriptive table there, just to save space. So you commonly encounter these forest plots, and they're a nice way of indicating the confidence intervals of different studies. Now, once the summary effect size has been calculated, as well as you would present the 95% confidence intervals to establish an upper and a lower bound, you then have to go about interpreting that effect size. Now, the metric used will depend on the type of effect being investigated. Either you're investigating group differences, say between treatment and control, between young and old, between employed and not employed, or you might be investigating the correlation between two particular constructs. Now, if your effect size is about group differences, for example, treatment versus control, then Cohen 1988 offered the following guidelines, which I'm sure you'll be familiar with. D less than equal to 0.2 is regarded as small. D less than equal to 0.5 is regarded as medium. D less than equal to 0.8 is regarded as large. Now, these are perhaps unfortunate choices for labels because it's very rare in psychology that we study seemingly large effect size, and even a small effect size can be very important in the right context. So I should just give my usual warning here that these were never intended to be more than yardsticks for the estimation of statistical power. They were certainly not offered by Cohen as a means of evaluating the practical impact of the effect. If you actually read Cohen 1988, which I rather suspect few people will, quite often it's cited by people who actually, it's quite clear, haven't read it. Cohen actually warned against this practice, saying that it was dangerous. So you really need to consider the typical effect size encountered in your discipline and your area of research. And you use that as the guidelines for evaluating the effect size. Likewise, if your effect is about a correlation, Cohen 1988 offered the following conventions. R of around 0.10 was weak. R of 0.30 is regarded as medium, and R of 0.5 is regarded as strong. Again, subject to the advice offered by Cohen that we should compare these to other similar effects in our field. For example, my area of research is human intelligence and cognitive ability. So when we look at the correlation between two intelligence tests, given that there's this shared common variance of G, it's not uncommon to have an effect size of 0.8, 0.9. Very, very strong effects. But if we look at other areas of psychology, so social psychology or organizational psychology, you very rarely see effect sizes that big. And so it would be quite unusual to see an effect size that big. You might be expecting something in the range of 0.10 to 0.2, 0.3, and that might be regarded as a decent effect size. So it all depends on your particular discipline and topic area. Okay, enough about effect sizes. But Rosenthal and DiMatteo, they did caution against blindly interpreting effect sizes by those thresholds. So see in particular in your reading there about the aspirin study and how even a small effect can have tremendous practical impact. However, I'm well aware, though, that incautious readers will likely go with Cohen's cutoffs anyways, because they're drilled into first-year students, and that's what people have learned. Or, and this is more likely still, they'll follow the lead of the meta-analysis. So, whatever they suggest the effect size is, big or large, trivial or very impactful, they'll accept that unquestioningly. Again, don't be like the sheep. Think for yourself. So some authors use linguistic hedges to convey that small means tiny or even trivial, and in the most egregious cases that it means zero or no effect. This is why these types of reviews can be dangerous for the unwary reader if you read it unquestioningly and without a solid foundation in statistics. So I'm going to present a cautionary tale of suspect conclusions, and it's taken from an actual meta-analysis that was rather high profile at the time. So consider the meta-analysis conducted by Hyde and Lynn, 1988, on gender differences in verbal ability. And we can see here the study published in Psychological Bulletin. Now, to set the context, gender differences in verbal ability are fairly robust and were regarded as one of the most well-established psychological effects. Now, the Hyde and Lynn meta-analysis had some interesting findings. Their operational definition of verbal ability omitted most language tasks where gender differences are largest, so grammar, spelling, and they did so without any clear rationale or even a definition of what verbal ability constituted. They also omitted key samples of educational assessments, and in one case they omitted effect sizes from one of Hyde's own studies. Why? We really don't know. Now, the summary effect size that they report in the abstract was small, d equals 0.11, but certainly not anything to be sneezed at either. But they concluded in the abstract, we argue that gender differences in verbal ability no longer exist. So it was certainly a controversial study and raised a lot of eyebrows at the time, but once it became published, it then became widely cited. Now, the effect on subsequent research was chilling, as new researchers read the paper, thought, well, maybe there's nothing more to be found here, it's gone away, this effect, so then they moved on to other topics. Yet gender differences in reading and writing are far larger than those for mathematics, which does receive a high profile. And so gender differences in language are grossly under-researched. And it took a considerable number of years before refuting studies were published that actually gave a complete view of the literature. Now, one of the other tasks in a meta-analysis is estimating variability across studies. In most cases, the distribution of effect sizes will vary due to factors such as sampling error, differences in sampling strategy, or demographic characteristics of the sample. Now, another goal of a meta-analysis is to quantify that variability and to determine the degree of what we call heterogeneity. Some variability, of course, is to be expected due to sampling error. But when we talk about heterogeneity, we're talking about variability that's due to other factors. Large variability points to the very high likelihood that a moderator may be responsible, and this possibility should be explored. Now, at a minimum, the author should present a statistical test of heterogeneity. In practice, though, this will almost always be statistically significant. In fact, some statisticians would say it's inevitable. And for that reason, they would advise people not bother with a formal test because we're going to find heterogeneity. And what is more important, in fact, is the amount of heterogeneity present. Now, this is typically represented by the I-squared statistic. Now, I promised there wouldn't be a lot of math, so do feel free to skip over this, but for the interested reader, here's the formula. So I squared is equal to Q minus degrees of freedom divided by Q multiplied by 100%. So it gives you a percentage, where Q is the chi-squared statistic of heterogeneity, and degrees of freedom is the degrees of freedom. So that's based on the number of studies that you have in a meta-analysis. Now the math involved is largely unimportant because you're never going to do it by hand. You'll let the computer do it, but it does give you a percentage score indicating how much variability is present beyond that which would be expected due to sampling error. So how do we go about interpreting heterogeneity? Well, there's various thresholds that have been offered for interpreting the degree of heterogeneity present across studies. Now I'm going to give you the following, which is a rough yardstick offered by the Cochrane collaboration. They're a large international consortium of medical statisticians who produce evidence-based literature. So 0 to 40%, that's minimal variability. In fact, you'll very rarely see such a low degree of variability in most studies because you're using different instruments, different ways of measuring outcomes, different types of samples. You'll see a fair degree of heterogeneity. 40 to 60% indicates moderate heterogeneity, and you'd certainly be wanting to have a look at that and see whether you could explain some of it. 60 to 90% indicates substantial heterogeneity. And as I said before, if you have a high amount, it strongly points to the likelihood of moderators. However, I should caution you that even if the amount of heterogeneity is small or even non-significant, it may still be appropriate to conduct a moderator analysis, particularly if you have some a priori hypotheses that you want to test about a potential study moderator. One other reason for understanding heterogeneity is the effect that it has on the summary effect size. So it can actually impact the way in which summary effect sizes are calculated, or rather the way that they should be calculated. Meta-analysis uses either a fixed effects model or a random effects model for combining studies. And I should just point out that just like you should come up with your hypotheses before you analyze your data, you should pick a model, either fixed effects or random effects, before you take a peek at that heterogeneity statistic. But if you do take a peek and you find that your model is incorrect, then you may want to consider switching. Excuse me. Now, the actual logic behind this is rather complex, and I won't bore you with the statistical theory, but a fixed effect model assumes that the true effect size in the underlying population is fixed, and so all the variability that you see across the studies in your meta-analysis is purely due to chance. The random effects model acknowledges that some sampling error is present, but also that there are other factors, so between study characteristics, that are also affecting the summary effect size. Why does this matter? Now, for a non-statistician, it's rather dull and boring, so it may not sound too meaningful. Let me just give you the Cliff Notes version. A random effects model permits you to generalize to studies not yet in the sample. And given that the meta-analysis is designed for use by psychological consumers who will likely want to evaluate a particular effect or use a particular intervention, you really want to have that flexibility to generalize to these future samples. So most studies now will go with a random effects model. Unless you have good reason for doing otherwise, I would advise going with it as well. Now, once you've done your heterogeneity analysis, you need to conduct a moderator analysis to try and explain away some of that variability. A moderator analysis should be performed to investigate sources of heterogeneity across studies, and usually you'll have an idea of what these might be. Now, there's two techniques you need to be aware of. The most common, and the one that you'll come across in pretty much every meta-analysis, is called subgroup analysis. What this does is compare different sample characteristics, like, for example, the developmental age of the sample, the socioeconomic status, or maybe the type of instrument used in either measuring the independent variable or the dependent variable. And then it tries to group these together and see whether that reduces heterogeneity. And the other technique is called meta-regression, and that's useful for investigating a continuous moderator. Things like maybe the publication year to see if the effect is growing over time or perhaps diminishing. Or if you're doing a cross-cultural study, you might look at factors like GDP, organisational size, things like that. So let's have a look at subgroup analysis. Now, in a subgroup analysis, what the analyst does is attempts to partition studies into related groups to determine if this reduces or eliminates heterogeneity. For example, we've got here a meta-analysis looking at visual spatial tasks, and what we've done, or rather what the authors have done, is indicated the overall effect size. In this case here we've got 0.56, but we can see there for different age groups there seems to be a developmental effect going on there. So for younger children the effect size is 0.33. This increases in adolescence to young adulthood, and then in older adults it increases further still. Now, in a meta-regression, we conduct a special form of the multiple regression analysis that we're all familiar with. But the variation is that each individual study comprises a data point in the scatter plot. So the study effect size is the criterion on the y-axis, and we code the target characteristic, for example, the publication year of the study, as the predictor. And we can see here a scatter plot. This is from one of my studies. I was looking cross-culturally at the size of gender gaps in science achievement, and I was looking at gender equality of individual countries. In more gender equal nations, where women are afforded greater freedom, we found that there were smaller effect sizes. So it actually reduced the gender gap. So that's one example with a scatter plot. But given the availability of space in journals, quite often you'll just see the meta-regression reported in text. So we've got here another one where we're reporting the z-test and the probability value associated with it. In this case, there was no actual effect of the predictor, so assessment year, and that was contrary to our hypotheses in that case. And that's a good way of testing whether there are changes over time by just having a look at the publication year. But certainly you can use many other types of moderators there, anything that is a continuous variable. Now the mathematics and stats involved is pretty trippy, I won't lie. It's not fun. You certainly wouldn't want to do it by hand. And I should point out too that not all commercial packages support meta-regression. But I suspect this will be changing and that we'll see increased usage in future years. So even if you're not likely to conduct a meta-regression, you should be capable of at least reading the output and the statistical results section and coming up with an assessment of it, rather than, again, just blindly accepting the conclusions drawn by the analyst. Now, moderators are important because they may suggest new directions. Often, the moderator of interest isn't apparent from just a handful of studies, but when you pull them all together across different types of samples, then a good meta-analysis can allow for testing new hypotheses or suggesting new directions for research. You, as a psychological consumer, should be aware of the important moderators for an association or that influence the impact of an intervention if you're going to be using it in your professional practice. So don't be that person who just has a look at the abstract. Go further and have a look at the results and make sure you can identify the important moderators if you're going to be using a particular intervention or studying a particular effect. Now, one of the other things that we need to do in a meta-analysis is to evaluate the impact of missing studies. So one of the criticisms of meta-analysis, or even individual studies themselves, is claims of publication bias. And some would suggest this is partly responsible for the replication crisis in psychology, because without the replication being part of the written record, we would never have known that some of these effects just wouldn't hold up. So publication bias refers to the tendency towards publishing statistically significant research findings, but they argued that null studies are rarely seen. It's also known as the file drawer problem, presuming that researchers' drawers are overflowing with unpublished data. Now, the meta-analysis usually calculates a file drawer calculation called the counter null. That's defined as the number of studies that would be required to render the summary effect in the meta-analysis to 0. And then the reader can assess the plausibility of this proposition having occurred, without anyone really noticing. That number is sufficiently large, and particularly if the number of published studies is relatively small, then it's extremely unlikely that there are dozens and dozens and dozens of studies out there that have been secretly hidden away or suppressed, or just sort of fallen victim of the tendency to publish significant findings. And you should also consider, as part of this, the search methodology that the meta-analysis employed, and in particular whether grey literature was included. Grey literature are things like honours theses, master's theses, postgraduate studies that just haven't made publication. It would surprise you, but there are many honours students and many master's students who will never go on to publish their research. That's a shame, because it means that the body of literature is smaller than it might otherwise be, and we don't get the benefits of the research they've conducted. But searching this grey literature, certainly most theses are online, can certainly help reassure you that the effect you're studying is real and the file drawer problem isn't an issue. Of course, there's more advanced techniques that we can use, and one of these that you'll come across is called the funnel plot diagram. So the funnel plot can be used to assess the possibility of publication bias. How it works is the funnel plot is a scatter plot of the effect estimates in each study, plotted against the degree of the study's precision. Now, you don't need to understand the statistical theory involved here, but it's fairly straightforward. The dispersion of effect sizes for smaller studies will be wider as they're less precise. So if you have a look at the bottom of the scatter plot, these should be fairly wide. And for studies that are larger, up the top there, it should be a much narrower range of values. In the absence of publication bias, we should see this effect. So there's much wider dispersal down the bottom than there is up the top. If there was not, that would suggest, the systematic suppression of these smaller effect sizes, and that would be a cause for concern. So if you don't see that sort of funnel type plot in your data, and you instead see something that's like an inverted funnel, that would be raising alarm bells. Now, a few other things that I'd just like to talk about before we finish are the meta-analytic reporting standards, or MARS. So because of the importance of developing competency in meta-analytic reporting, and given the rather shoddy studies you sometimes come across even today, the APA has issued guidelines on how meta-analyses should be conducted and reported. So this is the Meta-Analytic Reporting Standards, MARS. It's set out in the APA Publication Manual, and it's periodically updated as well in response to changes in meta-analytic theory. Another standard that you should be aware of is Prisma. So similarly, to encourage transparency in the way that meta-analytic search strategies are reported, and also systematic review protocols are made to the reader, Prisma has published standards for the transparent reporting of meta-analyses. If conducting your own, you're strongly advised to consult them. In fact, in a lot of scientific journals now, unless you're following the Prisma or the MARS standards, it will not be accepted for publication. So I'll just leave you with a few concluding words now about meta-analyses. Meta-analyses are responsible for transformational effects on the way psychology is conducted and the way research is evaluated today. When used carefully by a competent meta-analyst, they can provide greater precision than is possible for individual studies or even their replications. They can also shed new light on old questions by identifying important study moderators and experimental effects. That said, they must be interpreted carefully. The reason is that they are still subject to confirmation bias, to the ideological and the political agendas of the researchers that write them, the selectivity of the studies that they include, and also the quality of the studies that they include. So carefully reading the meta-analysis is important, and that's a skill that most psychologists currently do not receive training on. You have the responsibility to use it wisely. Don't be bamboozled by a meta-analysis author. Read it carefully, read the results section, and make up your own mind, particularly about the magnitude and the practical nature of the effect. So now I'm going to present you with the meta-analysis challenge. The dare, I'm posing it as a dare because I want you to actually do it. Read the assigned meta-analysis, either the org-psych one in the org-psych folder or the clinical meta-analysis. Hey, if you want, you can do both. And answer the summary questions. That way, you'll be able to put into practice what you've learned in this online module, and you'll also be able to see how your interpretation stacks up to mine. And remember, there is no right answer. It's up for you as a practitioner to evaluate the literature critically. So rather than have an expert tell you what to think, I would much rather you form your own opinion.